Good afternoon, ladies and gentlemen. We begin the technical session 31, vibration control session. I am Myung-ho Oh, professor of Mokpo National University. It's my great honor to chair the technical session.
I'm Jianguang Shi Jianguang from Xiamen University. I'm Irwin.
Okay, our first speaker is Chairman Irwin at RWTI. He will talk about human-induced vibrations in building. Please, Chairman Irwin.
Well, thank you for that introduction. It's good to see there are still some people staying here till the bitter end of the conference. I see the other papers in this session are on vibration control of the whole building, presumably due to wind and earthquake. This is a little different in that I was asked if we could provide a kind of background paper on human-induced vibrations in buildings. And so I turned to our expert in this area, Michael Wesolowski, who's the first author. And so he did most of the work in preparing this this paper here. And I have co-authors also John Galsworthy and Andrew Bell. So the outline of the presentation is, first of all, giving some background on floor vibrations and the impacts of unwanted vibration. And then we'll look at vibration criteria, and then methods of predicting floor vibrations. And then we'll finish up at the end with a case study involving rhythmic activity. And I think one of the impetuses for Professor Sang-Dai Kim asking us to produce a paper on this subject was there was a recent event in Korea where I believe it was a Taibo class caused a building to be evacuated because of vibrations that went through the building. Well, often the most common critical source of floor vibration on the upper floors of a building are human footfalls. But we shouldn't forget that there are other sources, such as mechanical equipment, construction or demolition of equipment of structures nearby, and then of course there's road and rail traffic. All these can be significant sources of annoyance, or even worse, within a building. And in recent years, with increasing improvements and use of very high resolution imaging equipment and laboratory equipment, the issue of floor vibrations has become even more pertinent. But and so this has caused a lot of additional research into the causes and ways of predicting these kinds of vibrations, which in turn has fed into more knowledge concerning the perceptible vibrations and human occupant comfort. Of course, humans are not nearly as sensitive to vibrations as some of the more sensitive equipment, but what we learn on the sensitive equipment can be applied to humans as well. Well, we've been involved in quite a few projects involving sensitive equipment, and the vibrations can cause relative motion between the internal parts of the equipment, or between the instrument and the specimen being examined. For instance, relative vibration between an MRI device and the person inside it, or with an electron microscope, relative vibration between the microscope and the specimen. And in healthcare and laboratory spaces, housing vibration sensitive equipment, the floor vibration can cause exceedances of the manufacturer's specified limits. And the reason they have these limits is, of course, you get substantial noise or errors in the measurement or in the image that you get out of the equipment if you have excessive vibration. And in the end, the reliability or performance of the equipment can deteriorate over time due to continuous vibration, and it can even throw off the calibration. And this can be, this can obviously be quite expensive to fix. Here's an example of an electron microscope image. On the left, we have vibration, or we have a limit of 6 1/8 micrometers per second velocity on the vibrations, and the image is at 65,000 times magnification, and it's an E. coli bacterium. The image on the right has got about 8 times that level of vibration, 50 micrometers per second, and if you look carefully you can see distinct degradation of the image, of the resolution. So this is just one example of the impact of unwanted vibration. And of course, besides vibrations affecting the equipment, if they're persistent and high enough level, they can cause fatigue and discomfort to staff and interfere, for example, with sensitive procedures, such as a surgeon undertaking delicate eye operations or brain surgery, and certainly one wants the minimal level of vibrations in those situations. And high levels of floor vibration can render spaces intended for those uses unusable. And this can be very costly to find out after you've built the structure, so it should be assessed early on. Well, over the past 25 years, generic vibration limits have been developing and evolving, and these are generally in the form of frequency-dependent sensitivities for different classes of equipment, and these kinds of criteria are used pretty extensively in the laboratory design for healthcare and research facilities. The vibration criteria curves have been developed and traditionally accepted as a basis for designing and evaluating the performance of vibration-sensitive equipment and the structures that support them. And here are some of the vibration criteria. The top-level curves indicate areas or are appropriate for areas where what's going on in that area is not particularly sensitive to vibration. And the traditional method is to divide the frequency range into 1/3 octave bandwidths. And the ISO criteria, those top 4 curves, are expressed in that format. And you could see in a workshop you've got, these are in units of inches, of micro-inches per second. You've got 32,000 is permitted. In an office, it's only half that. You halve it again for a residential unit during the daytime. In an operating theatre, you halve it yet again. And you would have even more stringent criteria if it's an eye surgery or brain surgery type theatre. The other curves below that are all other vibration criteria primarily intended for very sensitive equipment. And the bottom 2 to 3 curves are actually very difficult to achieve, but you do find some manufacturers actually requiring those kinds of levels, which can cause issues when you're trying to design to those levels, and it's often necessary to contact the manufacturer and say, are you really serious about these? And they will, in many cases, have one of their own experts look at it And often the answer is yes, actually, we don't have to be dead on. As long as you're close, that's good enough. Well, this is a table showing descriptors of these various criteria. And so, the top level, which is for a workshop, is that's 800 micrometers per second now. That's equivalent to 32,000 microinches per second. This is very perceptible, but in a workshop where people are undertaking heavy labor and so on, they won't notice this kind of, or at least it won't concern them. And then you have the next level down for an office where people are more sedentary. Obviously it has to be better for that, and so on down. You can see there's for an operating theatre, it's down to about 100 micrometers per second. And this is really getting down to the threshold of perception. And it's suitable in most instances. And for some magnifications of, say, on the order of 100 times, it's also adequate. But if you're doing eye surgery, you've got to be about 4 times more stringent than that. Well, over the past few years, imaging and diagnostic equipment has been improving, but as they improve the equipment, it makes the requirements for vibration criteria even more stringent. And equipment manufacturers are now often providing their own vibration criteria, not in the traditional 1/3 octave bandwidth, but over much narrower frequency ranges. And the manufacturers now, if they know their equipment's going into a given space, they will actually require proof of performance that the space is suitable. And the study has to be undertaken by a vibration consultant to prove that this site is acceptable for their equipment before they'll ship the equipment. Here's an example of one of the manufacturer's criteria curve as a function of frequency. And this is now in a Fourier transform format, so it's a much narrower frequency band. And the blue curve there is what would be acceptable for the ambient floor vibration for this equipment if it has the standard equipment isolation system. If you're prepared, I guess, to spend a bit more money and get an active isolation system or to retrofit it, then you can relax the criteria to be the upper curve, the mauve curve. That's just one example of trying to meet the manufacturer's requirements. In this example, that was specified in 0.125 hertz bandwidths. And this type of format for the criteria is becoming more common. And one of the effects of changing to this type of criterion is that it's much more unforgiving if you've got vibration sources that are very narrow bandwidth or have tonal qualities, such as mechanical equipment, because you'll get a very strong response over a very narrow frequency range. And this is converting that same criteria curve that you saw a couple of slides back. This red line here shows that curve converted to the more traditional 1/3 octave bandwidth, and shows it actually crossing several different lines of the other criteria. Well, this is an MRI machine, and this is an example, and I'm not expecting you to read this, it's in tiny writing, but it's all the small print that comes with this piece of equipment. And if you go into the small print, this is actually a lot of work to meet these criteria. And you may have a lot of trouble actually meeting them. And when you talk to the manufacturer and say, "Are you serious?" they will say, "Well, we'll have one of our guys look at it." And quite often they will say, "Yeah, actually, you're good enough," even though you didn't quite meet the criteria. So I guess they're covering themselves. Well, let's come from the equipment to human perception now. And we're talking about higher levels of vibration, and these are usually expressed more in terms of acceleration. So here are some curves that are again a function of frequency, and on the left scale you've got peak acceleration now rather than RMS as a percent of gravity. And it's divided into different types of activity. The most unsensitive vibrations are the top curve. And these are for rhythmic activities, such as aerobics or a disco, I guess, or Taibo exercises, as happened here. This is for shopping malls, dining and dancing spaces, offices and residences. And this is really the baseline for perception, again from the ISO standard. So the ISO standard is often used as a baseline curves, and then you apply various factors to this ISO baseline curve. And there are several standards that deal with this. The American Institute of Steel Construction has documentation on this in a standard. The National Building Code of Canada has documentation on it, and the Steel Construction Institute in the UK, and there are others. But they're all relatively similar. And what's important to note is that different people have very different tolerances for motion. The perception level of the most sensitive people is about a quarter of that, say, of the average person. Well, how do you predict floor vibrations? Human beings can be modeled as a mass, little m in this case, exerting a force onto the floor mass, which is m sub floor, and the floor is represented also by its stiffness and damping. And the American Institute of Steel Construction has a fairly simple methodology which makes it easy to use, and it's the most commonly used analysis method in North America to predict the vibration levels from footfalls. But as with any simplified method, there are assumptions made, and such as the structure has a uniform layout of bays, and it looks at the vibrations at the same location as the source. In other words, say the center of the bay, and only the natural frequency really matters. For complicated floors, the AISC method has its shortcomings, and it can be inconsistent and could result in overspecification in some instances. Well, the Steel Construction Institute and the Concrete Center methods, these are much more sophisticated. They do require the development of a full three-dimensional finite element model of the floors. And but these methods do allow you to develop a full multimodal time history of the response at any point on the floor, not just at the point of location. Then you can have different walking paths as well. So it's a much more comprehensive, although more complicated approach. And both the SCI and the CCIP methods are somewhat similar. One of the advantages of these methods is that the time history predictions can be processed into various, to compare with various types of criteria. So you can either compare with a peak-to-peak type of criterion, that's the peak up and down motion. You can put it into a 1/3 octave band format, or you can do a narrow band fast Fourier transform type of format. And also the responses can be predicted anywhere on the floor, and you can have people walking in any different directions. So you can basically map out the worst case areas of a given floor where you might have laboratory equipment or people working. And of course you can also extend down into different floors if your finite element model is extended to a group of floors. Well, I'm just going to finish up this talk, which has been more of a general background talk, with a specific case study of rhythmic activity in the building that RWDI looked at. And this was to examine problems caused by people dancing, I guess, or doing aerobics to music. And so they were doing typically 120 to 180 steps per minute. And this was a mixture of concrete and steel high-rise buildings with two floors devoted to this activity near the top. And so the finite element model was developed for both floors, and we applied the SCI method to multiple activity scenarios and locations. Between 12 and 80 jumpers were assumed. And this shows a result for different pacing frequencies with a couple of the criteria. One was for people doing weightlifting, and another one was for people actually doing the rhythmic activity. So we got 4% of G and 2% of G. And you can see the weightlifting criterion was exceeded at the upper end of the frequency range. And if we extended the possibility to going to more like 3.5 hertz, then we reached values that were even above the rhythmic activity criterion. So with this, it being this close, in this instance, it was decided to stiffen up the floors somewhat to bring those vibration levels down. And also this kind of response could result in the vibrations being felt further down in the building. Now the frequency is above the highest likely for jumping, but we felt it was still possible that you may have somebody who can jump a bit faster, I guess. So to conclude, obviously human-induced vibrations can have a detrimental effect on equipment and on the occupant comfort. Vibration criteria are still evolving to meet these needs, especially for the modern equipment as it gets more and more sensitive. And I've reviewed some of the predictive models that are available, which depend on the complexity of the building. And as we know, rhythmic activity has to be looked at carefully to avoid responses that could be felt widely throughout the building. So thank you very much for your attention. And if you have questions, I can't guarantee I can answer them all because this paper was prepared by Mike Wesolowski, who has more expertise than I do in this area, but unfortunately he was not able to come to present himself. Thank you.
If you have any question or opinion,
Thank you for your valuable presentation. My name is Len Chang in Dankook University. Well, do you have any design criteria or limitation or recommendation of the vertical vibration limit in Canada?
The National Building Code does have recommendations for vibrations for different uses. One of the curves up there, I think, was from the National Building Code of Canada. Typically, for say a footbridge, I think it's about 5% of gravity in that range. And for other spaces, it would be more sensitive, about half of that, perhaps.
Thank you.
Other question? Sorry. Okay, thank you. Thank you.